Hello students, so we are back with extreme value theory content. In this video, I'll review the threshold exceedances method. I'll review the first two subsections here. I'll leave the model fitting for a different video. So a bit of motivation. In the previous method we saw called block maxima method, okay, the previous section, what we do is we divide our data into non-overlapping subperiods of equal size, and then we focus on the maximum value in each subperiod. For example, if you're interested in the worst daily loss on the stock market in a given period, say a year, you would grab 1 year. Every day there's some gains or losses in the stock market. You take the worst day, and that's one data point. So it's the biggest loss, so it's a maximum of losses in a whole year. Now, if you want to do some fitting, some inference, you need several data points. So you can go back the previous year and the previous year, but you see, this is very wasteful of data, because let's say that you want 20 data points, you need to go back 20 years. Every year you take the worst loss, and then you end up with 20 data points. But to get 20 data points, you need to go back 20 years into the past. And so here, this is what this says. The practical usefulness of this can be limited because the length of data period is often limited. Maybe you cannot go back 20 years in the past, or maybe you would like 50 data points, then you go back 50 years in the past. Maybe the data doesn't exist, or maybe 50 years ago it's not representative of what it is today. So you see, by retaining only one data point out of a large number, we waste a lot of data. So another potentially better approach is to fit a specific distribution not to maximum, but to all exceedances over a suitably chosen high threshold. So in the example of the stock market losses, maybe you want to say that a daily loss of, I don't know, 2% or more, that's big enough. So then you're going to keep all the days that have 2% or more losses, and maybe then you'll have a bit more data. Now, this is still wasteful of data because you still disregard the data points that are less than 2% loss every day, but you could have more exceedance data than maximum data. And so here, in fact, this will be the crux of the problem to select an appropriate high threshold. What I mean is just let's visualize on a histogram. Let's say that you have collected some data here. What we will want to do in this section is understand the distribution of this. Okay, this quantity, or I should say this random variable, is what we often call big W. It is all the data points that exceed U, where U is some high threshold, given given they have exceeded that threshold. So here, if for whatever reason we decide that U is here, let's say here, just for the example, it looks like U is around, let's say 600. Then careful, we take the exceedance. Okay, so by what value does any observation exceed the threshold? So for example, if we have a data point at exactly the value 600, well, the exceedance will be 0. If we have a value at 1000, the exceedance will be 400, because again, we take the exceedance over the threshold here in this example 600. Okay, and here our mission then is to find the distribution of this W. And specifically, we want an asymptotic result. So we're going to let U grow to infinity and see what happens. Now, first things first, the punchline here is that exceedances will have the so-called generalized Pareto distribution. So sorry for the spoilers, but this is what's going to happen. The exceedances will be, at least in the limit, generalized Pareto distributed. What is this generalized Pareto? Well, it's probably a new distribution that you haven't seen before. So here we give its definition. By analogy, in the block maxima method, we had the new distribution, which was the GEV, Generalized Extreme Value Distribution. Now, this is yet another distribution that we call Generalized Pareto Distribution. And very important for you, do not confuse the two. Okay, they are different distributions. Okay, so the CDF is there. Now, in full generality, this distribution has 3 parameters. There's C, and we're going to try to interpret C in a second. And this is the shape parameter. So C really dictates how does the distribution look like. Then there's 2 other parameters that are mu and sigma. And you see in the expression, same as with the GEV, with this new distribution that I call GPD, you have kind of two definitions. One is for the case Xi is not 0, and one is for the case Xi is exactly 0. Now, why do we need those two definitions? It's just that here, if Xi goes to 0, if Xi is exactly 0, while this thing is 1 over 0, it's indeterminate form. So we need a different expression for the case Xi equals 0, but don't worry. This expression, if you do the maths, it's actually the limit of this one, the limit when Xi tends to 0. So in fact, this function, this h, is in fact continuous in Xi. And here, this is a CDF. So h here represents a CDF. Let's just have a look here at what is written there. Okay, the parameter mu can be anything. The parameter sigma needs to be strictly positive. Xi can be anything. But now careful that the support will depend on Xi. So when Xi is not negative, then the random variable here is defined for x's that are bigger or equal to mu. While if Xi is negative, then the support is here between mu and this quantity mu minus sigma Xi. Careful, if Xi is negative, sigma divided by Xi is positive. Sorry, minus sigma divided by Xi is of course positive. Now, what does this distribution look like? In essence, the bigger the Xi, the more heavy-tailed the distribution is. Well, yes. Firstly, if Xi is negative, well, if Xi is negative, we just said that then the random variable has an upper bound. In this case, yes, the distribution will be light-tailed because the random variable can never exceed a certain value. In this specific example, the upper bound would be 2. Okay, again, for the case Xi is minus 1/2. And then if Xi is either 0 or strictly positive, then the distribution doesn't have an upper bound on the support, I mean. But it's the case that if Xi is bigger, the distribution is heavier tailed. We can see this on the picture here. You see, for the biggest value of Xi, for large values, you see that the density is above the others. So yes, the probability of high outcomes, of extreme outcomes, would be bigger. So recall that in the GEV that we saw in the previous section, Xi was also dictating the tail heaviness of the GEV, and it was the same pattern. The bigger the Xi, the more tail heavy the GEV was. So now we have the same conclusions for the generalized Pareto. The bigger the Xi, the more tail heavy the distribution is. Small question here. If specifically mu is just 0, and if Xi is strictly positive, can you recognize this generalized Pareto to be, in fact, a familiar distribution that you know already very well? Well, yes, pretty simple calculations. Let's review them. If mu is 0, just, of course, replace mu here by 0. We're in the case where Xi is strictly positive, so we're in the case here. What happens to the CDF? We get this. Now, just a bit of rearranging. What we can do is just add change 1 for sigma divided by sigma, so that we can put everything over the same denominator here, sigma. Then when we do that, we can reverse the fraction so that we change the sign of the exponent from negative to positive. And after that, we just realize that if we multiply on the top by 1 over Xi and on the bottom by 1 over Xi, we get the expression here. And this is exactly a regular Pareto, well, a 2-parameter Pareto. Well, yes, you check your formula sheet. This exactly matches the Pareto with the parameter that we call lambda equal to this quantity, sigma over Xi. And the parameter that we call alpha is now this thing, 1 over Xi. So yes, this so-called generalized Pareto distribution, if mu is 0 and if Xi is positive, is the good old Pareto that we already know and love. Well, I don't know about love, but we know it. Okay, just here's some results for your reference. There's an appendix in the slides. You can check for the derivations of this, but we give you the first central moment and the second central moment, also known as the variance, of the generalized Pareto distribution. Oh my God, terrible typo here, right? Yeah, no, it's the GPD, Generalized Pareto Distribution. So sorry about that. I said before you shouldn't confuse the two, and I myself confused the two. So I'm sorry about that. But yes, indeed, those are the moments of the GPD. Now, just careful. If C is too big, then the expected value won't exist. Okay, so you do need C to be smaller than 1 for the expected value to exist. And same thing, if C is too big, the variance won't exist. Okay, which matches the idea we communicated before that for heavy tail distributions, the moment might not exist. And we just said that if C is too big, well, if C increases, the tail heaviness increases as well. Okay, so here, yes, indeed, if C is too big, we won't have the moments. Okay, so that's kind of setting the table. What we've done now is just we motivated the problem we want to have. Okay, we want to find the distribution of this thing. And the spoiler alert was that the distribution will be, at least in the limit, a GPD. And what is the GPD? Is this new thing over here. So now let's present the main result, which is going to be the Picklands-Balkema-de Haan Theorem. Okay, before we state the theorem, we have one more slide of setting up stuff. So again, our goal is to find the distribution of exceedances of observations above a high threshold. We call X a random variable with a certain distribution, a certain CDF, big F. Now, the high threshold will be this constant U. And then we define a new random variable that I presented before, this W, which is, so W here is what I call exceedances, because it's by how much does X exceed U, but given it has exceeded U. Okay, something we've seen quite a few times. One application here was what the reinsurer pays on an insurance claim that exceeds a certain threshold. Well, they would pay only the exceedance over the claim, but then this W would represent any positive payment that they make. Okay, so given a payment is made, what is the payment? That, of course, that's just an example. Okay, and again, as I said many times now, what we're interested in this is the CDF of this W. Now you might say, we know it already. Okay, we know how to compute the CDF of W if we know the distribution of X. This is the type of calculations we've done before. Here we give it a new notation. We say the CDF of this W given a certain threshold has been exceeded, U. We will call this big F U. So that's the CDF of the W. Now, maybe a different notation could have been FW, but then I don't know, I would have needed to write W given a certain UX, okay? So here, this is understood that big F of U is the CDF of this W, but specifically for a certain U, because of course the distribution won't be the same, usually won't be the same for varying U's. This is why we need a little U over there. We know how to compute it. By definition, it's simply the probability that X minus U is smaller than whatever the argument little x is. Okay, so little x here is just the argument of the function, but given, so under the condition that we know we had X exceed U. Now, this is just a conditional probability. You have probability of something, let's call this A, given something else, let's call this B. Okay, and just basic probability calculations give us this formula. So yes, we know the exact distribution of W. So why do we need more work? Why do we need some fancy theorems? Well, we would like to know the distribution if U goes to infinity, if U is extremely large. Okay, so we want an asymptotic result. And this is exactly what is presented in the next slide. So just before we present, we need to remember that the notation little xf is simply the right endpoint of f. So this is a technical definition, but you can view this as just the maximum value that the random variable can take. If there's no maximum value, which is the case for most of the continuous distributions we know, well, then xf is just infinity. Okay, for an exponential or a gamma or a normal or a log normal, there's no maximum value the random variable can take in which case xf is infinity. Okay, we're ready to present the main results. or the main result, singular, which is this theorem. Now, the theorem is stated there in mathematical rigor. It is a bit technical, but then I'll just review the theorem and then we explain what it means in English. So the result is this. So it's a theorem. We can find a positive measurable. Don't worry too much about this word measurable. It has a technical meaning in mathematics, but you don't need to worry about it. We can find a positive measurable function, sigma of u, such that the limit when u goes to the right endpoint of the supremum of this thing is 0. So this is true if and only if f is in the maximum domain of attraction of the GEV-C. Now let's explain a bit more. Here we have simply the CDF of our exceedances, the CDF of W as given here. Now we take the difference between this CDF of W and big H, which remember is the CDF of the GPD, the Generalized Pareto. Now, the Generalized Pareto, careful with a mu of 0, because here, this is how we define the notation. The first parameter is mu, so here we're simply saying, okay, the mu, don't worry about it, it's just 0. So we take the difference between those two things. Now the supremum, so a supremum technically is the smallest upper bound on a quantity, but just view this as the maximum, okay? The maximum value that, the maximum this can take for all the values of x here. So the maximum difference between those two things is 0 when the limit, when u goes to its upper bound. In words, this just means that if u is very large, this will be very close to this because the supremum, so the maximum difference between the two is 0. And this is a theorem, so this line here, the fact that in the limit when u is very large, this is very close to this because the supremum between the difference is 0. If that is true, well then f is in the maximum domain of attraction of the GV-C, but careful, it's the GV specifically with the C in this line. So what I mean is just the C here, the C inside the GPD is the same as the C here in the GEV. Same C. Now, it is a if and only if result, which simply means that it goes both ways. Okay, so I think you know if and only if means its implication in both sides. Meaning, if f is in the maximum domain of attraction of the GEV-C, then this thing is true. But also, if this thing is true, then f is in the maximum domain of attraction of the GEV. So in essence, here we're saying there's a very strong connection between the distribution of a maxima and the distribution of exceedances. Recall what maximum domain of attraction of the GEV means. It simply means that the standardized maxima of a sample from the distribution of f converges to the GEV-C. So basically, if the maxima converge to a GEV-C, well, then we also have that the exceedances converge to a GPD C with the same C. Hopefully that makes a little bit of sense. Let's review this slide of interpretation, but I think it's more or less what I said. If f is in the maximum domain of attraction of the GEV-C, if we increase u, the distribution fu, which is the distribution of the exceedances, becomes closer and closer to that of a GPD, specifically with a mu of 0, a certain sigma that depends on u. That's maybe a bit mysterious. We haven't said what sigma is, but we just know it exists. Okay, there is a certain function here, sigma u. But here, again, that's the important point. C, which is the same as in the GEV-C. Okay, so again, maybe we can give a specific example. In the block maxima method, we said that the standardized maximum of uniforms converges to a GEV with a C of -1. That's something we've shown in some of the examples there. But this means via this new theorem that we know for sure that the exceedances for a uniform, they will converge to a GPD also with a C of -1. So again, that's the point sorry if I'm repeating myself, but that's an important point. The Xi is the same, -1 in the case of the uniform. Now, when we talked about block maxima and the GEV, we said that technically it's not all distributions that are in the maximum domain of attraction of the GEV, which is true. But here I have a quote from the book, McNeil et al. It's not me who says that, it's them. Oh, I've lost my slide. They say essentially all the commonly used continuous distributions of statistics are in the MDA of the GEV, okay, which means that their exceedances will converge to a GPD. So because of that, this result, this theorem is wildly applicable. Yeah, for essentially all the common distributions we know, exceedances will be GPD. Okay, hopefully we've followed up to here. Now there's just a bit more of maths. And frankly, this piece of maths will be useful for the fitting method. Okay, the last subsection is called model fitting. But before we get to that, we'll just need a small additional piece of theory. So you see, in the theorem, the distribution of exceedances is close to the GPD with a mu of 0. So even though we define the GPD in full generality here with 3 parameters, in fact, we really don't care about mu, because the theory tells us that what the FU converges to, sorry, the FU here, what the FU converges to is a GPD with a mu of 0. So in reality, what we really care about, what we need, I should say, is a GPD with only 2 parameters, the sigma and the Xi. Okay, we don't care about mu. Sorry, mu. So because of that, for the rest of the video and the rest of the module, what we really need is this so-called 2 parameters GPD. Okay, 2 parameters GPD basically just means we have mu equals 0, and then in terms of notation, I'm just going to denote it. I'm going to drop the mu. I'm going to say h of sigma Xi is the same thing as saying h of mu is 0 and then sigma Xi. So the additional little bit of theory we need is this. Well, this bullet point here. If X is a 2-parameter GPD with a certain unspecified sigma and a certain unspecified Xi, okay, let's define FU as before. So the CDF of exceedances above U. The property is this. This FU is just the GPD. But now what happens to this GPD? It has a new sigma. There's a new sigma. The sigma U is the initial sigma plus CU. And then that's it. The Xi is the same. Okay, what does this what does this mean in words? If a distribution is already GPD, 2-parameter GPD, then exceedances are exactly 2-parameter GPD as well. You don't need any asymptotic result. Here, U doesn't need to be large. If X is already 2-parameter GPD, then exceedances over any threshold, again, U doesn't need to be big, will be exactly GPD. It's just that they have a new sigma parameter. The Xi remains unchanged, but the sigma is now updated to be, whoops, not a good choice of color. The sigma is updated to be this thing, which is function of the Xi. Okay, so in essence, we're saying for a distribution that's already GPD, we don't need asymptotic results. We don't need the big guns of this theorem, because exceedances are exactly 2-parameter GPD as well. Now the proof of this is here. It's not an especially hard proof, but still, let's review it. Now we do the proof for the case Xi is not 0. Well, yes, we need kind of 2 proofs, because remember that in the proof, of course, we're going to use the specific expression for the CDF, and the expression for the CDF is different in the case of xc equals 0. But let's assume we have xc is not equal to 0, and you can reproduce the proof, just follow the same steps in the case c equals 0, you should get the same result. Okay, this is what is written here. The case c equals 0 is similar and is left as exercise for the dedicated student. Yes, I am talking to you. Now, for the proof in the case of c is not 0, let's just start by the definition of f little u. This is what we had before. Simply replace, okay, we're going to replace the f by what it is. Here again, we assume that x is exactly a two-parameter GPD. So we replace here this is the fx. Okay, we replace it by what it is if fx is the CDF of a GPD. Now, some things are, well, there's some ones that cancel out, or because you might remember here in the expression, okay, we have a 1, but then because we're subtracting again the CDF, those ones are going to cancel out. Okay, we're left with this plus this, divided by this. Again, 1 minus something that has the 1 cancels out. Now we may realize that, lucky for us, this term is exactly equal to this term. Yep, so those you can just replace them by 1. And then this term you notice has the same exponent here as this one. So why not put everything to the exponent of -1 over c? And then what happens? Well, you may realize that same trick. This 1 plus cu divided by sigma, you have a 1, and then here you have a plus cu divided by sigma. So you can replace those by 1. And then I believe you should be almost done. You can multiply both sides, not sides, but the numerator and the denominator by sigma. When you do that, well, those cancel out. You're left with cx, and on the bottom, you're left with this. And you're done because you recognize that this is two-parameter GPD. Yes, look at this. It fits the general GPD. It's just that now we have a new sigma. The sigma is this, and the c has not changed. C is still c. Yeah, just have this in your mind for a second. Go back to the general definition and convince yourself again. We don't have a mu here. The mu is 0, and yes, we have this xc here, the xc here, and we divide by something. The something we divide by is no longer just sigma. It is now sigma plus xu. So we've proven the result. Now, maybe this result is a bit interesting in itself. Okay, you have a GPD, two-parameter GPD. I mean, exceedances are again GPD. Okay, good to know. But this result is useful for fitting. Especially, we are interested in the mean. We're interested in the mean of the exceedances. So recall the notation here. EU is the so-called mean excess loss function. And this, by definition, was simply, here we could have written, it's simply the expected value of W. Yep. This is E of little u is the expected value of W, but it's also, of course, the expected value of x minus u, given x has exceeded the threshold little u. Because we just shown that exceedances for a GPD are again GPD, well, we know very well what the mean of a GPD is. It was given by a formula over here. It was given by this, okay? So we know from this formula the expected value of the W. It's because we're in the case, remember, we're in the case where mu is 0. It is just the sigma parameter divided by 1 minus the c parameter. Okay, but recall that in our case, the sigma was now sigma plus c mu. This is why we say here that the value will be, well, the new sigma plus c mu sorry, sigma plus Cu, sorry about that, Cu, let's not confuse U and mu, they are different. And then divide by 1 minus C. Okay, now I've been talking a lot, but this really is the punchline. EU is a linear function of U. EU is a linear function of U. That's really what this whole little section, all those slides are trying to get at. EU is a linear function of U for the two-parameter GPD. And this is a fact that we can leverage when we fit exceedance data to the GPD. It really is helpful to help us find the appropriate threshold to do in practice when we actually do fitting. And what I mean by the appropriate threshold is simply this. We go back to our picture with the histogram. The theory tells us that if U is high enough, those exceedances, they should be approximately GV, and then that's quite practical because then we can fit the exceedances to a GV and use that in a model and make some predictions or things like that, right? But now, of course, the theorem is an asymptotic result. We don't know in practice what U to pick, U that is high enough, so the theorem applies. But because we know that the mean excess loss function is linear for a GPD, we can plot the mean excess loss function of our data and see at what point it looks like it starts to be linear and pick that point to be the threshold. Now, this is a bit abstract what I'm saying. I'll cover this in the next video. So in the next section, hopefully this is going to become a bit more concrete what I mean. What I mean when I say that you can leverage this fact. You can leverage the fact that EU is a linear function of U to pick an appropriate threshold in practice when you do fitting. But I will leave that for the next video. And I'll say bye-bye for now. Of course, if you have any questions, you can send them our way on the discussion forum. So I think I'll stop here and wish you all the best, of course. Bye-bye for now.